This is the first webinar of a 3-series webinar about debugging and special features of UDE. So the first webinar is today about Multicore and multi-controller debugging for the AURIX with the Universal Debug Engine UDE. And in 2 weeks, we look at some secrets for Python scripting, and the final webinar on 7th of April will be about analyzing the application's runtime behavior with some trace features of UDE. So let's get started. So in this webinar, we will have a look at UDE's multi-core debugging features. So I will show you these features on Infineon AURIX microcontrollers, but in general, let's say these features are also available for the other multi-core controllers that are supported by UDE. This is the first part. In the second part of this webinar today, I'd like to show you a special feature of UDE for systems based on AURIX. This feature enables synchronized debugging of 2 tightly coupled AURIX MCUs in a safety application. So before I demonstrate the features, I'd like to start with some general remarks on multi-core debugging. Before we can start debugging an application, we need to know how the multi-core system architecture looks like and how the software architecture that is running on such a system looks like, because that has consequences for debugging. So the simple software architecture that we know is certainly a single core application. And if you bring this onto a multi-core system like the AURIX, then you can run several single core applications in parallel on such a system. So each application has its own binary and its own ELF file compiled by a compiler and uses its own core. So there are no or only minimal dependencies between them. So debugging is quite easy. In most cases, you will focus on only one of the applications or only one of the cores at a time. So all the debug actions, that means run control, breakpointing, single stepping, and so on, should be performed only on the core in focus. The opposite case, that is a monolithic multi-core application. So you have tasks and functions that are distributed over all the available cores. We have close dependencies between the cores, and we need synchronization of the debug actions. All the cores must be stopped synchronously. For example, if the application hit a breakpoint, or if you are doing some single steppings on one core. If this is not synchronized, then you will get immediately an inconsistent application state. And then, of course, we have a mix of both corner cases. We have different code bases and binaries for the different cores. For example, for the AURIX, we have main cores based on the tri-core architecture and a GTM or an HSM. And for those special cores, typically a separate ELF file or a separate text file exists. And for this case, there may be also the need for perform debug actions only on a subset of the available cores. For example, only for the HSM or only for the tri-core based cores. So we need a kind of partial debug synchronization. What I have compiled for today's demo fits into the category monolithic application. So we have one ELF file containing a single binary which shall be loaded into the flash memory of the AURIX. This ELF file contains also all the debug information the debugger needs to show the source code, to know which are the variables and what functions exists and so on. The application that I have prepared is a simple cooperative scheduler on Core 1. That scheduler executes tasks based on a fixed time slots. The timer for this is provided by Core 0 so that we have a close interaction between these two cores. Just for your information, it's not that important for the demo. The correct timing behavior is observed, and if it's not met, then we get an alarm from the SMU, which is the safety management unit in the AURIX. All the other cores, namely core 2, 3, 4, and 5, are doing not very much except of executing some shared code that I need to show you another feature of our multi-core debug support. So executing or shared code means that we have the same source code, the same binary, but it can be executed by any core of the system. The debugger hardware setup looks like that, shown on the right side. We have a target device, which is a AURIX TC39 mounted on an Infineon triboard. The debugger hardware from our side is a UDE 2 Pro, which is the base device of our Universal Access device family. The Universal Access device family consists of 3 devices: the UDE 2 Pro, a UDE 2 Next, and a UDE 3 Plus that we will also see later in this demonstration today. The UDE 2 Pro that I use is connected using USB to my PC where the UDE is running, and it is also connected using this combined JTAG DAB Infineon target adapter to the DAB debug interface of the triboard. The JTAG DAB adapter is the only device-specific part in this debugger setup. That means the UDE 2 Pro, this applies also for the other devices that we have, can also be used for the other devices that we support. For example, devices based on ARM architecture, PowerPC based devices, or devices from Renesas like the RH850. You only need to use another adapter for those devices. It looks like the same here, and you need a different license to be able to debug such systems. Okay, then let's jump to the UDE, and I'd like to show you at first how to create a debug session. There are a few steps necessary, but it is quite easy. We call a debug session a workspace. So the first thing I'd like to do is creating a workspace. It is basically a file containing all the necessary information that you need for debugging. It's quite simple. We use the file menu, select new workspace, and then we define a name, for example, TC39 demo, and save it somewhere on your hard disk. Then we need a so-called target configuration. A target configuration says basically the debugger which type of microcontroller is connected, which type of debug interface should be used. It contains settings to prepare the target for debugging and something like that. You can do it from scratch using the new button, but I strongly recommend that you are using some of our predefined target configurations that we ship with UDE for almost all the evaluation boards that we support. And even if you have a own hardware, then start with these predefined target configurations and change the settings then as you need. So start with the default button, and then you get a list of all the available or supported microcontroller architectures. In this case, we have a tri-core AURIX second generation from Infineon. It's a tri-board with the TC39B step device mounted. And we select the tri-board, this one with the DEP enabled for the as a debug channel to the debugger. Press finish and then save it as a file. I take this default location here. So then we have a list of all the available target configurations that UDE is found in this folder here. I select this first one, which is the new one that I have created already, and then press OK. And then UDE asks you which course should be part of the debug session, or which course you want to see in the debug session. The default case is that all the tri-core based cores are enabled, and the GTM not. The GTM is the generic timer module, which is a Bosch IP and implemented on the AURIX. And because I have no code compiled for the GTM, so I can leave it untouched here. The HSM, which is also part of the AURIX, is not present here because for the HSM you need a special HSM package from us, and this package is restricted, and you need to get this package and the license a NDA from Infineon. So that's why the HSM is not present here, but we can of course use UDE also for debugging the HSM. So we have finished it, and then we can press OK, and then UDE connects to the target system. Here in the message window, in the log window, we see 6 successful connections to the 6 cores of the AURIX. So the inside the UDE, there are for each core specific core debugger available, which handles the communication to the specific core and also handles the symbol information or debug information for the code and for the data that assigned to the specific cores. But the complete system is visible in the UDE user interface, so you don't need to open another UDE instance if you want to debug, for example, another core of the AURIX or the GTM of the AURIX or the HSM of the AURIX. Everything is inside this common user interface. So what we need next is, of course, the target application. I can load this target application using also the file menu. Load program is the command. And then I look for the sample. I have compiled it with the tasking compiler, and the ELF file is located here in this debug folder. I open it, and then this window pops up, which asks you how to flash or how to program the binary into the target system, because the AURIX is after booting in a reset state, and only core 1 is in core 0 is in reset state, and all the others has to be waked up by the application. The only chance to flash the application is using the core 0. So that's why we check this blue checkbox here, which tells the debugger that the core 0 should be used for the flash programming. And we want to see all the debug information in all the core debuggers, as mentioned before. So the green checkboxes needs to be checked for all the cores. That means all the symbols should be loaded into all the core debugger instances of the UDE tool. So if I press OK, then I will be asked for a missing file or some missing files sometimes. This is the case if you have compiled your application somewhere else and not in the folder structure or file structure that it's used for debugging. In this specific case, I have copied the complete project to another location for this webinar today, and that's why the paths which are present in the ELF file are not correct anymore, and UDE can't find the specific or source files at the moment. This is not a problem, so I can ignore it for the moment, and I can change the workspace later on that UDE finds all the necessary source files. So I cancel this, and then automatically the Flash tool is opened because UDE recognizes that the application is programmed or located for the Flash. I can program it. Then I get this warning sometimes. And this warning is opened if you change the UCBs, some boot configurations for the AURIX. So this you should take very seriously, because you can damage your controller and you can lock out you from the debug port if you do a wrong programming here. That's why we pop up this warning. I'm sure that I have everything doing the right way, so I can ignore this or can press yes, I want to program also to use UCBs, and then the Flash programming is started and right now finished. I can press exit, and then we have a workspace that we can use for debugging. I can start the application. Application is right now running, and if I now break the application, then you will see that also we get this dialog here asking for some source files that are missing. I can ignore that. This is for each of the 6 cores necessary. And to avoid this behavior, I'd like to change some settings for managing the source file paths. So I go to config, debug server configuration, and then we need to change the source code behavior in the view server category. So we have 2 buttons here on the top. The first is aliases. These are all the ignored files. So they, I will delete them because I want to see them in the future. And then I have a path management button, which allows you to create some rules for path replacement. If I press this button here, then I get a list, or I can add a rule for path replacement. And here I get a list of all the paths that are found in the ELF file. We have here the first one looks very promising because it is a very general path here, and I can use it in this example for all the path replacements. Press OK, and then for this path, I need to define a replacement rule. I use this button here, and then I'd like to change the path I look for the actual location of my project here, which is somewhere here, and this one, that one. Okay, then I press OK, OK, can close this window, and then if I browse for maybe a main function here, or task function, maybe this one, then automatically UDE finds the appropriate source file. Okay, and then I can open other windows showing variables, registers, and so on, and then I start debugging. So I have prepared already a workspace with some more windows opened based on the same application. I opened this. I can save the workspace, of course, and I can use it the next day, or can copy it to another PC, and another colleague can use it for testing. So I have prepared one, same application here, same settings. The Flash 2 gets opened. You need to verify the Flash contents. It's the same application. We have no differences here, and I can close this. So then I can start debugging. What you see here are some windows showing source code, showing variables, showing register values, and so on. And each window is colored by a core specific color. So you see which window belongs to which core. So we have some colors here. You can see it on the status indicators here for each core, and you can see very easily which window belongs to which core. And also the variables that I have already browsed in are colored if they are assigned to a specific core. If they are not assigned to a specific core, then they are not colored, but here in this example, we have some variables that are assigned to a specific core. So you see which core belongs to which, or which variable belongs to which core. So then I can start the application. We see the application is running. We have some variables that are changing during the runtime, and we have some runtime refresh here, or runtime watches here. And also we have a register here, which basically is the register to control or to get the status of some of the LEDs on the triboard here. So if I break the application, for example, if I use a breakpoint, basically in the task 200 millisecond function here, then you will see that if I hit the breakpoint here in core 1, then automatically all the other cores are halted as well, synchronously. So we are here right now in core 0, and the toolbar indicates also that all the other cores are halted synchronously. This is the default behavior of multi-core debugging in UDE. From here, you can, for example, do some single steps, and then you see that all the single steps are performed in core 1, but also here in this example, also in we see it in core 0. So every time I do a single step here, basically the other cores are going into a running state and stop as soon as we end the single step in the core 1. If you want to break this behavior, for example, for a partitional run control, I mentioned this before in the slides, then you need to stop the complete system, which has been done right now, and then open the multi-core run control management of UDE, which basically controls how the synchronization is configured. And for that, we have defined a so-called run control group. And if I open this run control group, then you see that all the core debuggers, or all the cores of the AURIX, are part of this run control group. So every core which is part of this control group is synchronized for debugging. Then I can remove, for example, core 1. And if I start the application in core 0, then you will see, okay, core 0 is running and all the other cores are also running, but not the core 1. I can start core 1 also independently. And if I enable the breakpoint again, I hit the breakpoint in core 1, the core 1 gets halted, but the other cores are not halted. Can do some single steps here, and the other cores are not affected. That is partial run control or partial debug synchronization. And you can, of course, remove the run control groups completely. Then you have a complete independent run control and an unsynchronized debugging situation. Some hints for the AURIX. If you use run control groups, then core 0, the master has to be always part of the run control group. And if you want to change the run control group, the complete system has to be stopped. This is due to some hardware limitations. So because of this, I stop the application and switch back to the original state. So all cores are part of the run control group. Then I can start the application again. Everything is running. If I hit the breakpoint or enable the breakpoint again, then also all the cores gets halted. This is the first feature that I'd like to show. And the second one is how to deal with shared code. So shared code means code that is executed by not only one core, but several cores or all the cores. And you don't know which core is at the moment executing this code. So I disable breakpoint for that, start application again, and then I switch to another perspective in UDE. So perspectives are a very nice feature, which we introduced last year with the latest version of the UDE, which is the UDE 2021. And perspectives are completely user-defined and allows you to focus on a specific debug task. I use this here in this demo to show you 6 code windows, source code windows of the same location, the executed shared function for each core, but you can also use perspectives to define a kind of sub workspace for profiling tasks or for testing tasks. Or if you want to focus only on one core, then you can define a perspective for a specific core or for a number of cores. And then you can switch back or to switch back to another perspective if you change or if your debug tasks changes over the time. So in this case, I use the perspectives to show you 6 code windows of the same function here. And this is actually the same function because it's the same location. If I use the so-called mixed mode, then I can see here the addresses in the flash memory. Same for that one. Here is that these are the same addresses. So this is the same code executed only by different cores. Switch back right now. And if I set a breakpoint here in core 0, then we will only hit this breakpoint in core 0 because breakpoints are core specific. So we use so-called hardware breakpoints, which are a feature of the microcontroller in most cases. And these hardware breakpoints are only active for the specific core. If you want to halt also in core 1, for example, then you need to add a breakpoint here in core 1, and you see sometimes we hit the breakpoint in core 0 and sometimes in core 1. But this would be very annoying, especially if you have such kind of multi-core system like the AURIX with 6 cores. For that, we introduced the concept of multi-core breakpoints. I can change a already existing single core breakpoint by using the edit function in the breakpoint window for that breakpoint and check this multi-core flag here. And then you see the symbol has changed, and also we can unfold this breakpoint and see that we have a kind of breakpoint group of single core breakpoints at the same location in the memory. And right now we can start application, and we see we hold on every core which is actually executing the shared code. And that helps a lot if you have, for example, shared code like libraries and so on, and if you don't know which core is executing this shared code. Okay, with that, I end the first part and come to the second part. So UDE is also able to debug more than one controller at a time. By default, these controllers or MCUs are handled independently. That means that they are not synchronized for debugging. And this works, of course, not in all cases. So if you have, for example, such a architecture here, or such a this embedded system with two AURIXs, then you have basically two application scenarios with such kind of tightly coupled MCUs. The first scenario that we have is, for example, a safety critical system with redundant MCUs for ensuring the functional safety. So each MCU monitors the other one, whether it is alive and doing the right things. If you stop only one MCU during debugging and the other one keeps running, or you stop it sometimes later, then the complete system would be immediately go into a fail state because of this check if the other core is alive or not. So the debugger has a very bad impact on the application under test in this case. The other scenario that we have has the same problem. It is an application that is running on such a gateway board from Infineon. Here we have also two AURIX MCUs used, but not to get redundancy, but for extending the available resources, like adding some interfaces that are needed to add some computational power and so on. So in this application, we have two independent applications running on both MCUs, but they are also communicating very closely with each other. And when we have also some kind of a live check, then we have the same problem as seen before. The application gets immediately into an error state as soon as we break one of the both MCUs with the debugger. And for this, for these two use cases, we offer a special feature that allows you a synchronized debugging of both AURIX MCUs. as you already used to from Multicore systems, the entire system, that means both MCUs, is debugged within a single debug environment. So the look and feel is quite the same. And as we saw it in the demo before, and you don't need to add or open a new UDE instance for that. For the synchronization of both AURIXs, we have a additional debugger hardware that is needed. This is the UDE 3 Plus Multi AURIX debug adapter shown here. This is the additional hardware part. As shown here, this Multi AURIX debug adapter is connected to the debug ports of each of the AURIX. There are 2 DAP ports here on the board. We use for that the standard debug adapters for JTAG and DAP for the Infineon boards. And at the other side, we connected the system to our UDE 3 Plus base device. This is necessary because of the UDE 3 Plus is able to connect multiple targets at the same time. You can connect up to 8 targets. We have a cascaded concept here. We have these debug pods with 2 debug adapters that we are using here in this setup, and you can connect up to 4 of these debug pods to the UDE 3 Plus, so 8 in sum. In this case, we connected only 1 debug pod, which connects to the 2 DAP adapters or DAP interfaces of the target board, and in between there is our UDE 3 Plus Multi AURIX adapter here present. What we need else? We need else some trigger lines from the AURIXs. These are part of the AURIX package and can be used to connect the Multi AURIX debug adapter for debug synchronization. And this is needed to ensure a synchronization with a minimum delay. So it's not without a delay, but typically the delay is about 60 cycles on a 300 megahertz AURIX, and this is sufficient to ensure always a consistent target state of both MCUs. So if not, then your application has a problem. So then you have a very bad timing in your application. So in the application that I'd like to show you, or in the demo I'd like to show you right now, this is the hardware setup for that. I use this automotive gateway board from Infineon with 2 tri-core AURIX TC39. You can also see in this picture the Multi AURIX debug adapter connected using the 2 DAP adapter or DAP ports here using our standard DAP adapters. Here it's a bit closer, and also you can see here the trigger lines which are connected to an additional debug header for each of the 2 AURIX MCUs here. The application actually consists of 2 separate applications that are running on both of the AURIX MCUs. We have a high-speed serial communication between the 2 MCUs, and we have a safety mechanism implemented that the so-called master or MCU A checks if the MCU B is still alive. So this is the use case. And so switching back to UDE, I open a new workspace for this to show you. At first, an example where no debug synchronization is enabled. So we have get 2 times the program window opened for the 2 controllers here. You see the 2 controllers are present. So this is CPU A and this is CPU B, and we have 3 cores of both MCUs available here or enabled here to keep it to keep the overview. So if I start the application is running, and we have a LED which indicates the failure state. The LED is, I think, port 3 of this port register. I have put it here in the watch window, and this is low active. That means right now the LED is off, and if this value changes to 0, then the LED is on and the failure state is indicated. So I have a breakpoint here in this function in the slave core or the slave controller or controller B. And if I hit the breakpoint or I enable the breakpoint and hit the breakpoint, then you see that immediately the system goes into the failure state, because the core A checks if the core B is alive, and it's not alive anymore. And we have, if you go here into sort this controller A, then you see we are here in a kind of failure state, or a a endless loop from which you can't recover anymore. Okay, and to avoid this, we have to change our setup. I forgot to show you the Multicore run control management before. For this case, in this case, we have 2 groups for each controller A group. These are the controller 0 group, or for the controller A, and this is the group of controller B. So they are independent from each other, and that's the problem. I have already prepared a workspace that changes the behavior of the run control groups. So the same application looks quite the same. We start the application again, or not. I show you the run control group before. So the difference here to the other example is that we have all the controllers and all the cores in one run control group. That means if we start the application and enable the breakpoint again, then you will see that we hit the breakpoint in the controller B, but we are also hit the breakpoint or also hold the where is it? The controller A. So, and we can do some single stepping here, and you will see everything is synchronized, and you will never hit you will never get a timeout anymore. So you can disable the breakpoint. The LED is not on, so everything is fine. We can start the application again. We can enable the breakpoint again, can start it, and so on. And with this setup, you get always a consistent state if you do some debugging actions. Okay, and that's all that I want to show. What we have seen are the 2 cases. We have in the first example seen that when we have no debug synchronization enabled, we saw that the first MCU, that is the master MCU or MCU A, went into a timeout as soon as we hit the breakpoint. And in the second example, where we enable the debug synchronization for both controllers, the master controller was also stopped at the same time, and the breakpoint was hit in the controller B. We stopped in controller A as well, and we did not enter the timeout or the failure state. So the complete system can be debugged with this solution. And with that, I'd like to end today's webinar a bit over time. Sorry for that. If you have any questions, then please use the webinar panel to drop your questions there, or drop us an email if you like. In 2 weeks, we have another webinar about scripting with UDE for debugging and test automation. Thank you very much.